See, I'm forgetting my routine. Okay, so today is going to be the last lecture where we really cover big-time material about circuits. Next lecture, Thursday, is going to be about design. So I have, of course, some ideas of what we can design with what we've learned, hopefully something that you will find that is cool. But if you have something that you would like to design and maybe have some ideas or so, send me email and maybe we can look at that. Okay? So, but today we are going to talk more about operation amplifier. We sort of touched on them already in last lecture. Today we are going to get to the nitty-gritty and finish off this topic. So I will start with the recap, then go through basic configurations of things you can do with op-amps. I will show you how to use node voltage analysis to sort of using simple rules, analyze any circuit that we will encounter, at least in this course, that includes operation amplifiers. We will design finally a current source. Why? Well, because we need it for the touch sensor, right? That was something that we sort of swept under the rug. And if we have time, we'll do a few examples. So, recap. So, first of all, an operation amplifier has a symbol, and the symbol is a triangle, and it's got an output, and it's got two inputs, and it generally is used with feedback. And anybody remembers what kind of feedback? Turns out there are two different, when it comes to op-amps, there are two different kinds of feedback. Right. Anybody remembers which type of feedback we want to use with our operation amplifiers? Yes. Okay, we want to use negative feedback. So we're going to put something like this. Now, how do we make, so this is a feedback loop. How do we make sure that this is negative feedback? Anybody has an idea? Yes? Okay. Okay, we connect it to the minus terminal. So whenever there is a feedback loop, that means that there is a path where we can go from the output of the operation amplifier back to one of its inputs. And if we have such a feedback loop, we want that this feedback loop includes the minus sign. Okay? So, and then of course we have an output here. And over here we have an input. in, and that one needs to go to the other terminal of the operation amplifier. So negative. So then there is this idea of an ideal. And what are the characteristics of an ideal op-amp? Back there before you eat me. Okay, that's fine. Yeah. Okay, characteristics. One of them is infinite gain. Sometimes it's called open loop gain. And the reason this term open loop is used in conjunction with this infinite gain is that once we build circuits with operation amplifiers, very often we actually build amplifiers. Of course, we don't want to have a gain that is infinite. We want a gain that is 2 or 4 or 10 or whatever, right? And to distinguish from that gain, we call this one open loop gain. meaning without feedback. And then once we apply feedback, we get the closed loop gain. Okay? So this is one of the characteristics of an ideal operation amplifier. What else? What else? Yes. Okay. Okay, thank you. No input current. I in is equal to 0. Okay? And let me add one more thing that usually is not put together with operation amplifiers, but I just want to point that out. And that is, an ideal operation amplifier doesn't need a supply. If it's ideal, then what I've drawn here, this triangle with two inputs and an output, that's all we really need, okay? We don't need a supply. Of course, when you really go and use an op-amp in the lab, you need to connect a supply. And the reason I say this is that there was some confusion about, well, how does the supply affect my output and so on? Well, if the operation amplifier is ideal, it does not. The supply is immaterial, okay? So there is also another thing that we just have to be aware of. If we omit the supply, if we do not include the supply, then Kirchhoff's current law doesn't seem to apply for the operation amplifier. In other words, we get a current at the output, I out, that is non-zero. Usually, I mean, it could be 0, but and if I do not connect anything here, then it is 0. But the minute I connect the resistor here, then this current I0 out is non-zero. But the other two currents into the op-amp, they're 0, so we add all the currents and they don't add up to 0. So that's kind of a consequence of using this abstraction of an ideal operation amplifier. Just keep that in mind. But then, if you use the ideal operation amplifier abstraction, everything gets a lot easier, a lot simpler, and you can actually design complex circuits. Everybody, even very seasoned designers, they use this abstraction. Otherwise, it just gets sort of unnecessarily complicated. Okay. So, this particular circuit here is, it's already a circuit. It's an operation amplifier. Anybody remembers what this does? Yes. Okay, it's got negative feedback. But what does it do actually? What function would it have? Yes. Okay. So this particular circuit has V out is equal to V in. I call that V out. Okay? And so this is often also referred to as buffer. And last time we looked at situations where such buffers are useful, and you will encounter many more such situations in the homework and discussions or so, where you want to use a buffer. Even though it may sound sort of silly, we have a device that just replicates at the output what you feed it at the input. This is useful, and the reason it's useful is that this current here is 0. Okay, so that's really why we want that. Okay, so, but very often, of course, you don't want to have just a buffer, you actually want to have some gain. Yes? Can I clarify? Without RL. You could put an RL there, but then that would be sort of the job of the buffer circuit would be to drive this RL. It could be also a CL, or it could be a very complicated thing, a whole radio, whatever. Right. Okay. But, yes? So the question is, that loop there that I showed is not for the current, it's just to identify the feedback. The output current really, yes, it flows to whatever you connect to the output. None of that current flows back to the input, to that minus terminal, okay? because that current is 0. So if you connect nothing to the output of an operation amplifier, then the output current actually will be 0. But the minute you connect, you can calculate still what voltage you would have there and so on. You then can connect whatever you want to, and the voltage doesn't change, but the current will be now whatever current is required to maintain that voltage. Just at the output, an operation amplifier looks just like a controlled voltage source. Just like a voltage source, like a battery if you want, an ideal battery, except that it's controlled by whatever you have at the input. Okay? More questions? Yes? Okay, so again, is there a VSS and VDD? The minute you go to the lab, you better connect power to this thing. This is precisely like, who learned how to drive a vehicle? A car. Okay, most of you, I suppose, right? So if you think back when you first went, maybe you had a driving teacher. So, what did the driving teacher tell you? He told you, well, here there's some pedals. There is maybe a gear shifter or whatever. I told you about the stuff that you need to know to drive the car. He didn't go and say, hey, by the way, there is a gas tank and there is a fuel line and so on. If you don't put gas in, the car isn't going to run, right? He didn't start with that detail. So here it's exactly the same for the operation amplifier. If you actually go and use it, then you better give it juice to run, okay? Not gasoline, but electricity. But to analyze these circuits, to use operation amplifiers, we can abstract from that detail. And again, I recommend you do that. And one consequence is that you don't even need to show VDD and VSS. You don't even need to show it in your circuit diagram. And why is this a good thing? Well, because circuit diagrams have this tendency to get complicated. And we don't like complicated stuff because it confuses us, right? So we don't need that. So, again, when you're analyzing circuits, just forget the fact that you need to supply power to them. And once you go to the lab, you get a data sheet for the operation amplifiers that says, hey, there are these two terminals, and you need to put 5 volts on that one and minus 5 volts on that other one. Then you do that. If you don't, it's not going to work. It's just like a car without gas. Yes? Okay, so the question is, let's say you build a circuit that uses 10 or whatever, many op-amps. Can you use the same supply for all of these op-amps, or do you need different ones? Well, if you think about it, an ideal supply simply says the voltage is, let's say, 5 volts. And if your op-amp spec sheet says, I need 5 volts to operate properly, well, then it probably will be happy with that. Now, if you add a second op-amp, and that one also needs 5 volts, you can connect it there also. The other op-amp will not even notice anything because the ideal source will supply 5 volts, and that's that, and whatever current it wants. Right. So yes, generally, in fact, when we design stuff, the other problem is, of course, if you had 2 op-amps, one of them needs 5 volts and the other one needs 10 volts or so, then you would need 2 supplies. So one thing that we are not going to get into in EECS 16A, is sort of to arrange things that you need the minimum number of supplies, right? But those are all things that are very interesting, and they can keep us super busy and so on, and get us a high pay as engineers or so. But let's not get hung up on that stuff in EECS 16A, okay? Let's just make sure our first op-amp circuit works on paper and then afterwards in the lab. All right? Okay, so is that out of the way? let's look at the idea of gain. We want to get an operation amplifier with gain, so basically the goal is to build a circuit where V out over V in is equal to some gain, let's call it AV, and that's the closed loop gain. I mean, these terms are not super important. You don't need to know them to get a full score on the final exam. It's just helpful, okay? So for example, okay? Of course, you can make this gain any other number also, but let's say we wanted to build a circuit where the output is 4 times whatever voltage you put at the input, okay? How are you going to do that? Well, anybody has an idea? Okay, so I'll start with an idea. So the first thing is we better take an op-amp. Okay, so we know that the op-amp now, V out, is equal to AV, for in our example, times V in. Okay? We want this to be the case. That's the goal, right? That's our design goal. We also probably are going to connect the input to our operation amplifier. Otherwise, how could we possibly know what we want to amplify? So that makes sort of sense. V in, and out here we have V out, just to make this super clear. Okay, so the op-amp has 2 input terminals. Last time we called them, let's say this one is called VA and this one is called VB. I can give them whatever names I like, right? So VA, of course, happens to be what voltage? Happens to be V equal to V in, right? Because after all, we connected it to V in. So now, do you know the value of VB? Assuming that the operation amplifier is ideal, always in ECS 16A, and that we somehow will apply negative feedback when all is said and done, do you know what then VB would be? Actually, I just noticed that I need to go back to the recap. Here is V plus, and here is V minus, or could be VA and VB. The important thing is V plus is equal to V minus. If we have negative feedback and the operation amplifier is ideal, then this is met. That's the most important thing. In fact, some people call this the golden rule. Doesn't matter. Call it whatever you like. It just, if you have negative feedback and the op-amp is ideal, then the voltages at the 2 input terminals, V plus and V minus, are equal. Or VA or VB, with this nomenclature, they're going to be equal. Now, we haven't put our negative feedback loop yet, okay? We're going to get there. But we know that if we're successful to create a negative feedback loop, then these 2 voltages are equal. So in other words, VB is equal to how much? This is equal to V in. So the voltage here is going to be, if we were to measure this, we would find that this voltage is going to be V in, and that of course also is equal to V out divided by AV, for in our example. Okay? That's the condition what we started with. V out over V in is AV, well then means that V in is equal to V out over AV, over 4. Okay? Fair enough. Okay, so apparently that's the thing. So now we just need a way to tell the op-amp that we want this voltage to be a fourth of V out. Do you know of a circuit that can do this, that you can take V out, and from V out it can produce 1/4 of V out? a voltage divider. Hey, you know, these things are useful, not just for the exam. They're truly useful as circuits. Okay, so we have two resistors, or 1 and or 2, and we want that this voltage is here is going to be V out over AV. If, for example, this would be 1/4, then we could use 1 ohm here and 3 ohm. This isn't the nicest omega. 3 ohm for R2. And if you use your voltage divider equation, which I'm sure you're not familiar with, you get 1/4. Okay? So once we do that, there is only one thing we have to do now. We have to make sure that we got negative feedback. So I neglected to put pluses and minuses here. Where should the plus go? At the top, and the minus therefore goes to the bottom. So here we designed a circuit that amplifies the input by a factor AV, and for these values of resistors, for example, AV would be 4. Okay? So by the way, when you actually build this, you're probably not going to use 3 ohm and 1 ohm resistor, but it would work just as well, actually better, if you use 3,000 ohm and 1,000 ohm here. Why is that preferable? Anybody has an idea? Yes. Okay, it will consume less power. So obviously there is going to be current flowing through these resistors. If they're very high valued, the current's small. If they're low valued, like just 1 or 2 ohms or so, the current is going to be very large. Since this current here is anyway 0, we don't need to run a large current down there. We only need to get this voltage. We don't need to supply a large, or any current for that matter. Okay? So we're going to use high-valued resistor. We're not going to waste power, otherwise it's just heat. Yes? What is actually... What does it mean that the current is 0? It just means that the current that flows into this terminal here, that current is equal to 0. And likewise this current here. If you were to insert an ammeter into the wire that you connect to the input of the op-amp, you would find the ammeter reads 0. Now, obviously, if you could have another circuit. You could have a circuit like this one, where you have how do I do this? You could have a circuit like this one, a not so good op-amp. Okay, so in the triangle is an ideal op-amp, but then outside the triangle we have sort of a bad op-amp. And now, this bad op-amp, there very, very well could be current flowing here. You might even have another resistor here that goes to ground or so. You would buy a bad op-amp or so, then there might be current flowing. I don't know whether this is helpful. I mean, all I want to say is that we could certainly have also some kind of a contraption where this current wouldn't be 0. But in ECS 16A, the operation amplifiers all is ideal, so then these currents are 0. Okay? So, on the final, or whatever, on the exam, please do not get confused. The current's going to be 0. So, okay? All right, so, does this make sense? If you had to build a circuit that takes the voltage and amplify it by a factor of 10, would you know how to do that? Okay, good. Okay, we know how to do this. All right, so now we're gonna try something. Now, in this circuit, we connect the input here, right? That's where we connect the input. Well, let's try to connect the input instead over there, okay? Yeah, we just connect the input in, if you want, in the wrong place and see what happens. Okay, so and what happens is called inverting. Okay, so let me redraw the circuit a little bit. So our new V in now is over here. Okay, so that's this V in. And apparently it's connected to the negative terminal of the operation amplifier through this resistor R1. Okay? We're just redrawing the circuit. There's nothing new. You have everything on this page. There's nothing new. And then there is this resistor R2 that goes between the output and the negative terminal of the op-amp. So let's put R2. And then the old input here, well, we could apply an input there also, but you can do this with using superposition. So let's just set this for 0 right now. Okay, so that's simple. And the output is over there. Okay, so now we have a new circuit. It's different from this one because we put the input here instead of putting the input there. Okay, and otherwise, it's exactly the same. I just redraw it because it's easier to think about it. So now, I would like to know what is V out. Okay? And now we have to do circuit analysis with an operation amplifier. So I'll let you try to do this. Take a couple of minutes, 2-3 minutes, wake up, get paper, and try to do this. And then we sort of work it out together, okay? But I would like you to try first, okay? So try to, what is it exactly what I would like? What we want? We want an equation that says V out is some function of V in and the resistors R1 and R2, okay? And we want to know what this function is. Okay? So you can start doing KVL or KCL or whatever, right? And knowing that this is an ideal operation amplifier, try to analyze this problem. Okay? Already know? What is the current flowing here? This resistor. Ah, see? Okay, now you can solve it. Little hint. What is this current here? Try to figure that out first. If you're stuck, try to figure out what is this current. Okay? What is the value of this current? Anybody has the answer already? Anybody who wants more time? Who wants that we work together now? Okay, so we'll work together, all right? So first, what do we have to do first? What's the first step if we analyze a circuit with an op-amp? Well, we have to determine if our conditions are met. The first condition is that the op-amp's ideal. Well, that's always the case in EECS 16A. Okay? The second thing is we have to verify something about the feedback. What is it? Negative feedback, right? Here we have negative feedback because if we go through around the loop here, we go through the minus terminal. So we have negative feedback. Great. Okay, so if we have negative feedback, then what was this big rule about this volt? Actually, we are in this one here. This one here. What is this rule about these two voltages? They're the same, right? They're equal, meaning this voltage here is also equal. And so again, it means that if you went there with the voltmeter, you would always measure that the voltage here with respect to ground is zero. It doesn't mean that there is actually a wire connecting the two. If you put the wire there, it's not going to work anymore. Okay? So don't put the wire there. Even without the wire, if we have negative feedback, the voltage here is going to be zero. Well, once we know that, can we figure out what is I1? This I1 here? It's just equal to V in over R1, Ohm's law, right? We have V in across that resistor, and the value of the resistor R1, Ohm's law. Okay. So then, this current flows out of the resistor. What is it going to do next? Okay, it's going to flow up here. The current here is going to be I1, and the current here is going to be 0. And the voltage here is 0. Okay? Really simple. So, what's the voltage across the resistor? Let's call this voltage V2. Yes? Okay. Yeah, you're absolutely right. It's going to be I1 times R2, right? And then, of course, we can plug in for I1. So, what is the voltage here? That's the only tricky part. The voltage here is 0. The voltage across here is V2. Then maybe we can use KVL. We start from here. We do a KVL loop. Let me do this in a different color. A KVL loop like this. Okay? So we start from 0 and we go right back to 0. Okay? So KVL should apply. So then we enter at V2 at the positive terminal. Plus we enter V out also at the positive terminal. And that completes our loop, right? So this is simple KVL. And therefore V out is equal to minus V2. And that is equal to minus I1 times R2. And that is equal to minus V in times R2 over R1. Okay? So now we've analyzed our circuit. Hey, it's kind of interesting. This also is a gain stage if you want. It multiplies the input with R2 over R1. But there is this minus sign here. And that's why it's called an inverting. Sign inverting. Okay? It does sign inversion. Sign inverting gain stage. So, sometimes you use this one, sometimes you use the other one. In fact, we will see shortly an example where we use both of them simultaneously. Why? Well, because then we can use it to calculate the difference between two voltages. So there is one other thing that I want to point out. Here we have the input, and what's the current that is drawn from the input source? Whatever we connect to the input of this gain stage, this happens to be non-inverting. What is this current here? It's going to be 0. I is equal to be 0 because it's simply connected to the op-amp, therefore the current is 0. What about the current here? This current here is I1, which is also equal to Vin divided by R1 for this circuit. So it's not 0. Okay. So sometimes you absolutely want it to be 0, but with the inverting gain stage, you don't get that. Yes? Why is I1 not equal to? Because the voltage across this resistor here we have Vin, here we have 0. The voltage across the resistor is Vin. Right? The voltage here, this voltage here is 0. So the voltage here is 0. The voltage here is 0. So the voltage across the resistor is just Vn. Oh, there is voltage drop across it. The R2 has to be present, first of all, so that we have negative feedback. And secondly, the current I1 flows through R2, and we get a voltage drop in R2. And that voltage drop is precisely the amplified version of I1. Well, I1 is the same, but I1 is proportional to Vin, and then if you make R2 larger than R1, the same current produces a larger voltage, and consequently we get gain. So we want this resistor here in order to produce the voltage V out, but the current I1 is determined solely by Vin, not and R1, not by R2. Okay, maybe talk to me after the class. Okay. So again, let me get back. In this, for the inverting gain stage, there is current flowing into, not the amplifier, but into the input of our inverting gain stage, I1, current I1. Sometimes you don't want that. What's an easy fix if you don't like this, and you still want to use an inverting gain stage? What could you do? Yes. Exactly. Just put I'm running out of space here, but you could put a buffer in front here. In fact, I'll draw a buffer, but it's going to be a very small buffer. Minus, plus. You could put this here, okay? If you did that, now this current here still would be I1, but this current here would be 0, okay? A little bit small, but it will work. Okay, so now some of you may have found that analyzing this circuit was a bit convoluted or difficult or I don't know what. So I promised you that just like for any other circuit, we can use node voltage analysis, and analysis becomes simple. We can actually do the same with op-amps. NVA, node voltage analysis for op-amps. So what's this? Well, it's a technique that works. A computer can do it. That works on any sort of circuit with op-amps that we encounter in Eleng 16A. And you just have to sit there and crunch and you get the result. I promise you, learn this technique. You probably can use it on 3 problems, or I don't know exactly yet. on the final exam, and you get 3 points, okay? Just for learning this technique. So please learn it, and don't complain it's hard. It's just, a computer can do it, and you are not a computer. You are much smarter than that, okay? So, let's figure out what it is. So, let's do it for an example. And also there will be a note posted on the website. Today maybe it's already there on the course website. And it goes through exactly this, it describes this technique. But anyways, we're gonna go through it all together. So, okay, very complicated circuit. So again, it may already be on the website, and if not, this afternoon it will be on the website. This circuit, the whole analysis, and nicely typeset and so on. So you can refer to that, just like the node voltage analysis handout that was posted at the beginning of module 2. Okay, so so the rules are pretty much the same as for normal node voltage analysis. We have to identify a reference node, ground. We have this already in this circuit, so nothing big there. Then we have to identify all the nodes for which we know the voltage already. So that would be this one, that's an input. Well, we know the voltage there. Otherwise, the circuit is not going to work. If you don't tell it what it should amplify, how could it know? Okay, so these are known. We don't need equations on those. And then, and this one is special, the output of an operation amplifier. Well, I'm not saying that we know the voltage there, but you don't write an equation for that node. Okay, so that's special for op-amp. No equation, no KCL equation for V out. Okay? I need one less equation. And then all the other nodes we have to write equations. So in this particular case there are 2 more nodes, this one and this one. We have to write equations for those. And then further, let's call this V minus and this V plus. Further, we have a new equation that we normally don't have. We have that only with an op-amp. V plus equals V out. Right? Ideal op-amp. Oh, and just be sure, don't forget to check we have negative feedback. Yes. Okay? So once we have that, now all we need to do is we need to write 2 KCL equations. We need to write a KCL equation for this node, and we need to write a second KCL equation for that node there. We'll start with this one. Actually, I'll let you write the KCL equation for this node here, for the V minus node. You will write the KCL equation, then we are going to work it out together. So, but get started, hey, otherwise I will be nasty and I will not give you the answer. You have to read a 200-page book to get it. Who has got the KCL equation? Yes. Okay. All right, perfect. So IR1 is equal to that? Plus 0, yes. So, okay, so equation 1, that's for node V minus, is the sum of all currents leaving the node is 0, right? That's what KCL is. So IR1, we defined up there what that is. IR1 is equal to IR2 plus, if you want, plus 0. We need to put that there, right? Okay? Fine. Now let's replace this. I mean, there was this step 5 to 7 or so in the NVA handout, but let's do this just using Ohm's law directly. What is IR1? Well, this is going to be equal to the voltage on the left side of the current arrow. That's V minus the voltage on the right side, minus the voltage on the left side, minus V in minus divided Ohm's law by R1. And that is equal to IR2. Well, that is going to be equal to V minus the voltage on the left side, this time, of the current arrow, minus the voltage on the other side of the current arrow, minus V out, divided by R2, Ohm's law, right? And then we also get a second nodal equation. That's the nodal equation here. You can either write the nodal equation or you can recognize this as a voltage divider and just write down the result from the voltage divider. Because this is an NVA example, we are playing computer, we're gonna actually write the KCL equation. So it's going to be V plus minus V in plus divided by R1. It's a different R1, but it has the same value. Okay, is equal to V plus over. No, this is not true. It's equal to minus, right? The sum of all currents leaving must be 0. All these two currents are leaving, and here we also have this current and this current, they're leaving. So the sum of these better be 0. Okay, so in the handout it's correct. And I fixed it here too, thankfully. Okay? So the sum of all currents leaving is equal, or the sum of all currents leaving a node is equal to the sum of all currents entering that node. That, of course, would be the same thing. Okay? So you get these equations, and then if you try to solve them, what do you get? Whatever the term was, you're missing one equation. You don't have enough equations, so you're not going to get a result. And what are you going to do to actually get a result? Because after all, that's the point of the analysis. Where do you get an additional equation from? Exactly. So the third equation, 6, is V plus is equal to V minus. And then you do some analysis, and what you get is V out. So this is solving linear equations. Module 1, you know this, you can do this in your sleep, so we're not going to. It's going to be equal to V in plus minus V in minus times R2 over R1. Okay? You have this circuit here, and what it produces is an output voltage that is equal to the difference of whatever you apply at the input, multiplied with the factor that's equal to the ratio of R2 over R1, which of course you can choose by putting in appropriate resistors. Extremely useful. Okay, extremely useful. Very often you have that. For example, you have a bridge circuit that scale or whatever, and that we had a little demo on. You can use this circuit to amplify that voltage. Pick it up and amplify it. Okay. Be careful that the current flowing into these terminals is not zero, because there are these resistors here. Okay. So if you want zero current, what do? Well, you put a buffer out in front. Okay. You have a question? Or just need for oxygen? Yes. So this current here is non-zero, right? This I or 1, let's say, or minus, this current here is minus I or 1. That is going to be equal to, minus V in minus over R1, right? Anyways, this current here, this current before we called this one I1, and this current I1 is equal to V in minus over R1. Okay? Oh, you're right. Minus V minus, yeah. I did it for V plus equals 0. Okay, but you're right. Okay, anyways, the point is that this is not equal to 0, okay? Generally, it's not equal to 0. And in many sensor applications, you really can't pull current from the sensor. It's going to take the wrong measurement or so if you do, okay? So in that case, you want to do something so that the current into this contraption is 0. That flows into this contraption is 0. So now I'm going to do another trick. Don't rip your laptop apart. But so what we can do is we can put a buffer here. And we apply V in minus prime, we apply that here. And this current is equal to 0. And the current that flows into this amplifier, I1, that is going to be supplied by the buffer. And here we have a current that is not 0, but here we have a current that is 0. And if you had a bridge circuit here, we've had these bridge circuits, right, where the resistors, they measured something, for example, the weight of something, or and then you analyze this circuit a million times, VDD, VSS, or whatever, right? And you want to know this voltage here. You want to know this voltage, and you want to amplify it. Well, you can use this circuit for doing this. But if you connect this circuit here without any of the buffers, you're going to pull current out of these nodes. And that will change the voltage drop across the resistors, and probably changes the very voltage that you're trying to measure. Not good. So you put the buffer one here, you put another one here, and now the current is 0 because the buffer supplies the current, but the buffer itself doesn't take any current at the input. Okay, I'm glad I helped with that one. You had another question?
Yeah, could you explain how you got the out again?
How I got this V out? Okay, so this was some work. I simply solved these equations, right? We had an equation 1, an equation 2, we have an equation 3, and now it's just crunch time. Okay, so you just need to solve these equations. I didn't do that in front of class because I can't anyways. Yeah. Yes. Precisely. So the question is, the op-amp does a little bit like the voltmeter. It measures what it's supposed to measure, but it doesn't affect the circuit. Right. So again, that's absolutely true. It does not affect the circuit because there is no current flowing in. So but the minute you apply other elements around the op-amp like this R1 here, you got to be careful. Now it's no longer true. But you can fix it by just using another op-amp here, where you don't have any of these resistors. And now the current is going to be 0 there. Yeah. If we add the buffer, we need what? Yeah, so I'm not sure I understand your question. We apply the input voltage now here. We don't apply it here anymore. Yeah, we just add the buffer and we leave this away. That's why I call this V in prime. This is our new input. That's really where we connect the input, whereas the buffer generates this other input. Yeah, good question. Yeah. Yes. This one. So look, I mean, if you had, it's like water. If water is leaving this node and water is leaving that node, if that water all was positive or so, then all the water would even. No, I mean KCl. I'm not sure how I can explain this, but maybe the water doesn't work for once. It just the sum of all currents flowing out of a node must be equal to the sum of all currents flowing into the node. Yeah. Yes. The sum of all currents leaving the node must be equal to the sum of all.
That I is referencing when you add the buffer. In this case, I equals negative IR1.
No, this is just IR1, and this was IR2. So this is wrong here. IR1 plus IR2 is equal to 0. Right? The sum of all currents leaving the node is equal to the sum of all currents entering the node. There is nothing entering the node, so the sum of all currents leaving the node is IR1 plus IR2 is equal to 0 because there is nothing entering the node. Yeah. Okay. Well, thanks. You just leave me just enough time to deal with the current source. Okay, but yes, I'm sorry that I wrote this first wrong, but now it's correct. So, current source. So, we will take this as a design problem, okay? Simple design problem, warm up for next lecture, Thursday's lecture. We have to design a current source now. Wow, that sounds difficult. Well, what are we going to use? Well, we need a source. But if we go to Radio Shack or whatever, a company that isn't bankrupt yet, and we buy a source, a battery or whatever, they will not have a current source for us, but they will supply us a voltage source. So we'll start with the voltage source. So we have a voltage source Vs, okay? Now we want the current. Well, what element could we use to generate a current? Well, a resistor, R. In fact, what is the current? Well, the current IR is going to be equal to Vs over R. And it's even constant as long as we don't change the value of R, that current is constant. So it is actually easy to generate a current IR that is constant. There's just one little rub in here. What's the rub? Yes. Yeah, okay, but it's a perfect voltage source, so the voltage source stays constant, the resistor stays constant. We get that current, the current is constant, we can adjust the value of it, just use a different resistor, we can get any current we'd like. But why can't we use this in our touch sensor as a current source? Yes. Yeah, I mean, if we were to put our touch sensor somewhere in there, then the current would change. Putting it another way, the current there is just perfect. It's just how we're going to get to it. I mean, it disappears in this ground and then it's not very useful anymore. We somehow would like to have a ground node that acts like a ground. What does this mean? Well, the voltage is always nice and zero and doesn't change, but it doesn't just eat up all the current that we dump into it. That sounds kind of crazy. Does such a thing exist? Yes? Yeah, somehow I think you're up onto something, a buffer or something like that. Look, if we had an operation amplifier and we put this terminal to 0 volts, right? This is 0 volts, we connect it to ground. What is the other terminal here? Once we apply negative feedback, would be 0 volts too, right? So we put our current into this 0 volts, okay? So we take our resistor, put that here. We take our source, Vs, put that here. And what is the current that's flowing here? Well, that's IR, and that's equal to Vs over R. Wow, that's good. And now we want to do something with this current. Well, we need to close our negative feedback loop anyways. So now I have negative feedback, and the current flows into, let's call this resistor RL. Or X, whatever name we want to give it, doesn't matter, okay? It's not a baby. It's not important, okay? So just give it a name. Okay. Let's say this resistor was 10 ohms. I ask you, what is this current here? Let's say that this current, let's call it also IL. What is the value of this current here? It's going to be equal to IR. It's equal to Vs over R, right? Now let's change this resistor, make it 100 ohms. What is the current? It's actually exactly the same. It doesn't matter, right? What RL is, it doesn't matter. The current there is simply going to be equal to IR. The op-amp makes sure that that's the case, because it keeps this voltage here nice at 0. But the current cannot flow in the op-amp, therefore it has to flow through whatever we connect here. So this acts like a current source. The current in RL is constant. Precisely the definition of a current source. Now in our touch sensor we had a capacitor and we wanted a constant current flowing into our capacitor. Well, we just replace RL with the capacitor. So touch sensor. See touch. And over here we have a resistor and we have a voltage source. This is 0, consequently this is also 0. Okay? And the current that is flowing here is going to be Vs over R, and it doesn't matter at all what C touch is. We have a current source, we have a touch sensor. Hey, slick. And all we need is an op-amp, a very simple circuit. So in the lab, you replace Vs with a square wave, and you have a box that does this for you. I have a function generator. You use this for Vs that puts let's say plus Vs and minus Vs alternatively. Okay, and then this is really the source. You replace your constant Vs with that thing. You put the resistor here. You put the op-amp. In the lab, don't forget to hook up VDD and VSS. It's not going to work otherwise, but you just hook it up correctly. Don't mix them up, otherwise the thing gets very hot and you can burn your finger. So you put the capacitor, C-touch, here, just to the output. And you also will need to put the second resistor there, and we talked about last lecture. We talked about why we need that resistor and so on. You just put it there, and they tell you what value needs to be. It's in the lab instructions. Okay, and so that's your circuit. And then you look at V out. V out is going to be this triangle. Okay, that's V out. And the amplitude of the triangle is going to depend. If there is a finger present, it's going to be small. And if there is no finger present, well, then it's going to be larger. And there is actually a thing called oscilloscope. You have one in the lab. It's like a TV, but it's much more interesting and much more expensive. And it shows you these waveforms, okay? On the screen, you can look at them. Oh, this one's a square wave, and you connect the other one, and you get the triangle, okay? And you can see the triangle gets bigger and smaller, and depending on the size, you can determine, yep, touch, no touch. Okay, so that's how this thing works. So now we designed something. We designed a current source. It wasn't that difficult, right? Are there questions? Yes.
So someone in discussion yesterday asked what happens if you put two current sources in series. Now that we know how to build a current source, what happens?
So what happens if you take two current sources you put in series? This one is 1 amp, and this one is 2 amps.
And so the TA answered that it depends
Okay, so what happens? Look, first of all, normally we treat current sources like op-amps or so here, or voltage sources, we treat them as ideal. And that doesn't exist. Okay? So then if you actually went to the lab and you somehow built current sources, then yes, they would have limitations, right? They would fight. This one would say 2 amps, and this said, no way, it's 1 amp. And so this one would make its voltage as large as you can to force the full 2 amps through, and this other one would say, no, even you can make the voltage 1,000,000 volts, I'm not going to run more than 1 amp. And maybe one breaks, or maybe there is a fuse or whatever, something. Okay, so, I mean, it's a fine question, but, you know, the circuit makes utterly, absolutely no sense, so why bother building it? And it's just, again, so within the scope of EECS 16, I would just love it if you learn this NVA, node voltage analysis technique for operation amplifiers. Then I'll feed you circuits that are not nonsensical, and you analyze those. Right? I mean, this is kind of the same thing as you have a 5 volts, and you have 10 volts. It's again, I mean, it just get your EECS degree first, and then with all the great salary that you make, you can study philosophy, okay? And then you can ponder questions like this, okay? But first, do something very practical, get an engineering degree, okay? And my advice, free, okay? Okay, I'll see you Thursday. If you have ideas, burning ideas of what we need to design, send me email. Depending on what it is, I'll do my best.